If you believe that life is mechanism, you will be a believer in the clockwork homeostasis. It's literally inconceivable to believe otherwise. Obviously, I think that's a mistake, because doing so is to confine your thinking about life and its nature to within a conceptual bubble. And it's a bubble that excludes, in my view, a coherent theory of life and its distinctive nature. Anthony Burgess expressed this dilemma in his classic novel, A Clockwork Orange. It's been described variously as a crime novel, a dystopian novel about youth violence, about psychiatric abuse, and the overweening power of the state. Read the book. It's a brilliant novel. But the title is germane to what we're discussing here. Lots of people have asked Burgess what he meant by the title, and here are his words. A clockwork orange has the appearance of an organism lovely with color and juice, but is in fact only a clockwork toy to be wound up by God or the devil, or parenthetically, since this is increasingly replacing both, the almighty state. In other words, Burgess was talking about what we might call the mechanistic fallacy, that you can build mechanisms that resemble life, but these never will be life. His broader point was that a philosophy of mechanism is to accede to a philosophy of confusion, and to Burgess, that confusion leads inexorably to totalitarianism. We needn't go that far, of course, but the basic critique remains. Mechanism can only ever be a pale imitation of life itself. It can only ever give us a fundamentally confused understanding of life. So let's take a deeper look at the concept of the clockwork homeostasis, how it's been tested, and how it's stood up. Our focus will be on the biocybernetic approach to temperature regulation in animals, which I introduced in the last chapter. A biocybernetic approach to body temperature regulation was initially very successful. Scientists located very quickly what they supposed were the elements of a negative feedback controller of body temperature, a thermostat, in a part of the brain known as the preoptic anterior hypothalamus. Well, that's a mouthful, so we'll just abbreviate that as the POAH. If you draw a line through the head just in front of the ears, the preoptic anterior hypothalamus will be in the middle of that line. All the elements for a negative feedback controller seemed to be present there. So, for example, scientists located temperature-sensitive nerve cells in the POAH. In some, the activity would decline with local temperature. And in other neurons, activity would increase with hypothalamic temperature. These were supposed to be the brain temperature sensors, which were thought to feed into a neural circuit that would encode the sensed body temperature. Also to be found in the POAH were temperature-sensitive neurons whose activity would vary according to a kind of threshold. Some would be active until temperature reached a certain level and then would switch off. Others would be inactive up to a certain temperature and then switch on. These were thought to feed somehow into determining the set temperature. The encoded sensed and set temperatures could then feed into the neuronal equivalent of a comparator, which would take that information and encode the output to control effectors for both heat loss and heat gain. In short, the elements of a thermostat all seem to be contained within the POAH. All these elements together would operate as a negative feedback controller. For example, artificially heating up the POAH could trick it into thinking the body temperature was too high, just as you could, say, by holding a candle flame under a wall thermostat. The body's heat loss effectors, like sweating or panting, would then kick in, even though the actual body temperature was normal. It worked the other way too. Cooling the hypothalamus artificially tricked the POAH into thinking the body was too cool. Shivering and increased production of metabolic heat would follow, even though the actual body temperature was normal. All nice and tidy. Body temperature seemed demonstrably to be regulated by a clockwork mechanism in the brain. But science, if it's working properly, always destroys its own neat theories, and this was the case here. The more the workings of the POAH thermostat were looked into, the more complicated the whole system seemed to become. Other thermostats kept turning up in the spinal cord with their own sensors and separate negative feedback systems. There was also an extensive array of skin temperature sensors for both warm and cool temperatures, sensors in the viscera and in the muscles, and these could all feed information into the spinal cord and hypothalamic controllers, influencing their performance. And skin temperature, for its part, seemed to be regulated independently of the brain and spinal cord thermostats, suggesting there were negative feedback controllers there as well. And to make things more complicated still, these different negative feedback centers could interact with one another, each manipulating the activity of the other. We're at the point now that researchers suggest that even individual cells have the ability to manipulate and control their own temperatures. You can see the implications of this. The more it's tested, the more granular the clockwork thermostats are becoming. There's not one cybernetic machine regulating body temperature, there's a multitude of them. And here's the irony. The granularity has become so fine that we have now converged on the many little lives doctrine, right back to where things were at the end of the 18th century. The clockwork homeostasis, in other words, has been undone by its own internal logic. We see here a dynamic similar to the attempts by classical and medieval astronomers to prop up the Ptolemaic conception of an Earth-centered solar system. Just like the Ptolemaists had to keep layering on ever-proliferating epicycles to the orbital paths of the planets, an endless proliferation of cybernetic temperature regulators had to be layered on to make sense of how the system behaved. And with a similar end, an overly burdened model that has collapsed under its own weight. The clockwork homeostasis idea remains appealing, though, in part because it offers a framework for thinking about problems differently. That's what we as scientists are supposed to do, after all, think differently. Let's take fever as an example. What is it? How should we treat it? Traditionally, physicians have regarded fever as pathology. Where it was encountered, the proper therapeutic response would be to suppress it. Patients with high fevers were sometimes immersed in cold water baths, for example, probably the worst thing a physician could do. The clockwork homeostasis idea has turned this idea on its head, and let's see how. Here's our basic clockwork model for temperature homeostasis. We'll add a dial with a scale and an indicator for a set point. Let's fix the set point at the normal body temperature, and let's follow the typical course of a fever. Prior to a fever's onset, the body temperature, indicated here in blue, oscillates around the set temperature, indicated with a red dashed line. With the onset of an infection, body temperature rises. In terms of our biocybernetic model, the fever is essentially turning up the dial on the thermostat, that is, increasing the set temperature for body temperature regulation. In response, the heat gain effectors, like shivering, are activated, and for the patient, the onset of a fever is accompanied by a perception that the body temperature is too cool. The patient feels a chill. Tuck that perception away for the moment because we'll return to it soon. The body temperature then tracks the elevated set temperature, as we expected should in a negative feedback controller. When the fever breaks, this can be thought of as the set point going back down again, with the body temperature tracking along behind it. This activates heat loss effectors, like sweating, and the patient's perception of the body being too hot. In the biocybernetic conception, then fever is a regulated state. There's nothing wrong with the body, it's just regulating temperature around a different level. The biocybernetic conception of fever prompted physicians to rethink their medical wisdom. Physicians no longer try to suppress fever, except when the fever is so high that it threatens the patient's life. But the biocybernetic model of temperature regulation also subverts the whole idea of the clockwork homeostasis. Here's where we come back to that perception that the body is either too cool or too hot. We're familiar with fever in animals like ourselves that use internally generated heat to maintain body temperature. This we have in common with other animals like mammals and birds that also have very active internal furnaces, so to speak. Those animals also get fever and through similar mechanisms like shivering or sweating. Most animals, like lizards, for example, don't generate enough internal heat to affect body temperature appreciably. But surprisingly, these creatures also get fevers. They don't shiver or turn up the internal furnaces, so to speak. Their fevers are behavioral fevers. Behavioral fever can be consistent with the biocybernetic model for fever. We just need to tweak the effectors. Rather than generating heat to warm the body, for example, lizards seek heat in the environment. And by the same token, rather than having heat loss effectors, lizards will seek cool environments. In this way, a lizard can sustain quite high and steady body temperatures. So, for example, a lizard can seek heat by basking, sitting on a rock, say, exposed to the sun. Alternatively, the lizard can seek cool by sitting in the shade of a leaf. To sustain a high body temperature, a lizard can move between these two habitats. If a lizard moves from the shade to the sun, it warms up. If the lizard moves from the sunny rock into the shade, it cools down. And here's how temperature regulation works there. The temperature of the hot environment is marked by this red dashed line, and the temperature of the cold environment is indicated by the blue dashed line. The lizard spends some time in the hot environment, shaded yellow, warming its body. It then spends some time in the cool environment, shaded blue, and its body cools. In this way, its body temperature oscillates back and forth within a fairly narrow band. Okay, that's interesting, but what about fever? We know lizards get fevers. How do they do it? As we can for mammals and birds, we can imagine fever arising from an increase in the set point of the lizard's clockwork thermostat. But how do they get hot? Well, they do so by changing the schedule of shuttling between the hot environment and cold environment. Specifically, the febrile lizard will spend longer in the hot environment and less time in the cold environment. The lizard's body temperature will still oscillate back and forth, but now at a higher body temperature. Voila! Behavioral fever. Problem solved. Well, not so fast. Behavioral fever is a physiological state, fever that arises from an exercise of choice, how long to spend basking on this nice hot rock. This throws the whole idea of the clockwork homeostasis on its head. And let's remind ourselves of what Anthony Burgess himself said about the title of his book. A clockwork orange has the appearance of an organism lovely with color and juice, but is in fact a clockwork toy to be wound up by God or the devil, or since this is increasingly replacing both, the almighty state. The clockwork homeostasis is predicated on the notion that homeostasis is the outcome of the operation of a machine. That is, it's a clockwork toy to be wound up. Fever in an animal like a mouse can be interpreted as tweaking the dials on a cybernetic machine. Turn up the thermostat and fever follows. The state follows the mechanism. But let's remind ourselves of the radical implication of Claude Bernard's notion of homeostasis. It's the mechanism that comes from the homeostasis and not the other way around. What's missing from this point of view is any answer for what's actually winding up the toy. Behavioral fever in an animal like a lizard is hard to reconcile with the notion of a clockwork homeostasis. To get a fever, the lizard has to seek out warmer temperatures. The fever is therefore more the lizard's desire for a high body temperature than it is the operation of a machine. What's missing from the clockwork homeostasis is a good idea of where the desire comes from. And as we'll see in the next episode, there is a rational answer to this question, and it's inherent in Claude Bernard's notion of homeostasis as a fundamental property of life. Before we get there, though, I'd like to share an example that bolsters the case that homeostasis is a form of active desire. Animals, like lizards, are behavioral thermoregulators. They maintain high and steady body temperatures by seeking out sources and sinks of heat in their environments. In so doing, they can attain a degree of body temperature homeostasis that is the near equal to what one sees in, say, a mouse, or ourselves, for that matter. Cognition and striving appear to play important roles here, as they appear to do in behavioral fever. Let's start with an open, sunny habitat. Scattered throughout this habitat are numerous spots where a lizard could go to bask in the sun and so elevate its body temperature. There's an ecological twist here. A basking lizard is easy to see. Any small boy can tell you that. And this exposes a basking lizard to an elevated risk of being seen and perhaps picked off by a predator. What should the lizard do? Well, it has to assess its risk somehow. In an open sunny habitat with many places where a lizard could bask, these risks are low. The lizard could bask at any of the abundant basking spots that are scattered around the habitat. A predator will therefore have a hard time locating the lizard, and the risk a basking lizard faces is commensurably low. This also means that the cost to the lizard of maintaining a high body temperature is likewise low. Okay, let's turn to a different habitat, a forest, where most of the habitat is shaded. The sun comes through the canopy in a few isolated sunflecks. The lizard can only bask in these sunflecks. Basking to raise body temperature is therefore a considerably riskier affair. A predator looking for a lizard to eat need only stake out one of those rare sunflecks. The cost to the lizard of basking is therefore high. Sunflecks are rare, and there's a large distance between them. Lizards' regulated body temperatures differ between these habitats. In the open, sunny habitat, you will typically find that lizards maintain high and steady body temperatures. In the shaded habitat, the regulated body temperatures will be lower and more variable. This pattern is difficult to reconcile with the clockwork homeostasis idea. Where is the temperature set point in all of this? Well, there seems not to be one. Rather, the lizards appear to be making a costs and benefits assessment of their habitats and adjusting their behaviors accordingly. The body temperature the lizard sustains is therefore more of a cognitive assessment of an environment, mediated through the intentional seeking of the sources and sinks of heat in an environment. Could it be, then, that the clockwork homeostasis idea is exactly backwards?